So in the beginning, we talk about femtoseconds. So what is a femtosecond? Here you can see a time scale for different amounts of femtoseconds, and you see that the age of the universe is on the right side in the range of 10 to the 15 to 10 to the 18 seconds. And now we're talking about exactly the opposite. We're talking about femtoseconds, which is 10 to the minus 15 seconds. These are the shortest events you can generate with a laser at the moment. So just for a comparison, light, or what is a femtosecond? Light travels from the Earth to the Moon within roughly a second. To pass a human hair with a thickness of around 66 micrometer, it takes only 100 femtoseconds. And if we're now talking about the difference between continuous beam and femtosecond pulses, I show you here a sketch where the continuous wave laser has an average power which is more or less simply always on. So, and if we think about a laser which is always on in time, so by Fourier transformation, this means that the frequency is really narrow. So then typically you can think about a single frequency. This is a so-called CW laser. If we now go to femtoseconds or to pulse lasers in general, you can just imagine that for the pulse laser, we squeeze the light into a pulse, and the pulse are separated, and within the pulse separation, there's more or less no light, so the laser is completely off. So by using the Fourier transformation, if we want to have a very short time event, we will have a very long broadband frequency range. And this is characteristic for ultra-short pulses we'll see in the next slides. So if you compare pulse durations to the optical spectrum, you always have to keep in mind the Fourier transformation, which means if you have a long pulse, which is on the right side, at the top you have a long time event, which means you have a narrow spectral wavelength bandwidth. And if you now come to a very short pulse, a short time event, you have to have a very broad band frequency range. So therefore you can just keep in mind, if you want to have a short femtosecond pulse, you have to have a lot of frequencies which are emitted at the same time. On the left side, you can see that there's always a factor which gives you the correlation between time bandwidth product, which means there are different factors for Gaussian shapes or other shapes for the pulses.